Good evening and welcome everybody. This is Obi-Wan Pez for Ensimplex Pachinko. We are doing a math night. So, if anybody has anything they want to talk about tonight, feel free to drop that in the chat. I will be open to I will be competing with the jukebox. That's a bit better. Right, I will be looking at a few different things tonight. I have Euclid's Elements that we can work on for a bit. We got several of the other books that have been kind of kicking around. Don't know what anybody else feels like, but it's the kind of things that I've got. Hey, 26 stacks. Absolutely. Anything in particular, or just like start from the beginning? Start from the beginning, you got it. All right. So, we know that when we were talking about trying to solve equations, right? We're trying to get different kinds of numbers. Quadratics in particular started out with this notion that some number, when we square it, is going to get us something like 9. Okay, so simple enough here. We could have guessed right from the beginning that, okay, well, if I take 3 and plug it in, square it, I'm going to get 9. So we know this to be true. Now, there's also another answer that we don't really often talk about, and that is negative numbers. So this was something that also did not exist going all the way back to the beginning of human history. Negative numbers are somewhat difficult to talk about in terms of like what they mean and where did they come from and things like that. So we kind of take it for granted nowadays that we have this number line and it extends infinitely in both directions. 0 in the middle, 3 on one side, negative 3 on the other. Indian mathematicians, on the other hand, pretty much always knew that negative numbers existed, and so it's because it was part of their philosophy that at least, this is the thought anyway. It's been a part of their philosophy in Hinduism that everything is an endless cycle of birth and death, that you have this symbol, shunya, which represents the never-ending circle of life, death, rebirth, all that. The European mathematicians, on the other hand, simply knew that basically the only things that existed were from here on up. Reason being, again, not 0. But everything above 0 existed. So they had, all integers, fractions, decimals, all that. They just thought of it only in terms of positive numbers. Why exactly? Well, as it turns out, the idea of nothing to Europe was kind of an aberration. They believed that an absence of number was tantamount to an absence of God. And since they couldn't have any dirty, filthy atheists in their country or in their civilization, they just kind of ignored it. It went completely by the wayside. And so something like 3 minus 4 really had no meaning to them. Or rather, what would happen is you'd say, if I have this and I owe this, then I just owe 1. So the direction of the number, the positive versus negative bit, really is taken over by English, or whatever language they used in their particular location. So in Europe, they did not allow for a negative number. So again, Europe. Europe doesn't allow this, or at least didn't. No, they were perfectly fine with integers. Or, well, okay, I see what you're going with there. Yes, they have the natural numbers, so our counting numbers, and all of the positive reals. But they didn't have 0, and they didn't have any of the negative reals. So this kind of stunted growth in mathematics for many centuries. And for a lot of their quadratics, it kind of did the same thing. Instead of, and this was also true a little bit in the Middle East, when they first invented algebra, the inventor of it, Al-Khwarizmi, ended up creating books which contained quadratics that would say something like, if you have the square of a number plus 3, and that equals the number we're looking for, this would be a form of a quadratic that we would try and work out. This would not be written as, in Europe or the Middle East, would not be written as x squared minus x plus 3 equals 0. So they wouldn't do this until like the 14 and 1500s. So way, way, way in the future. So this is like 14 to 1500s Italy. Is like the first time where they start doing this, like seeing an inkling of this. Okay, so moving on. What we then have is we have here also we know that there's a negative number, -3, which when you square it is going to get us 9. So the proper way to do this is to say that we have x squared is equal to 9, and we take the square root of both sides to undo the square. So squares and square roots are inverse operations of each other. They undo each other. This then produces, and I'm kind of a stickler about this with my students, but this produces the absolute value of x is equal to the square root function can only return one value, 3. So the absolute value of x is equal to 3. So then what does this mean in terms of the number itself? Well, usually you're pretty used to just putting a plus minus on the other side, which works. Because on the number line, what we're going to do is we're going to say that there is this x value, and really what we're doing is we're trying to find the distance between x and another number. In this particular case, it's x and 0. You try to find the distance between those two numbers. So this ties into something that I've been teaching in absolute values for a while. I just started doing this with my classes today. Or I started doing quadratics with my classes today. So always very fun. So the idea here is that we want the distance between x and 0. So this is what we get here. The distance between x and 0 is 3. So 0 is here. X is an unknown value. And we know that the distance has to be a distance of 3. So there are two places where we can go. One higher, one lower than 0. Over here we have 3. Over here we have negative 3. And since this is equal to, we know that we have to go exactly that far from 0 to get to our answer. So x is going to be equal to, in this particular case, a positive or a negative 3. And yeah, you could probably just jump there. Your teacher is probably used to that by this point. And would say like, okay, yeah, from the square root of x squared, you just get x, and from the square root of 9, you get plus or minus 3. Sort of. So the square root of 9 is only 3. This is why the absolute value thing is actually kind of important. Not absolute value. This is the square root function, which again only returns one value, so one output. And here the absolute value is telling us that we don't actually know whether the thing on the inside of the square was a positive number or a negative number. It could have been either, because we squared it. And so now that information about whether or not we started with an x value that was positive or an x value that was negative has been destroyed. So x squared destroys the information about x in terms of its sign. So we don't know. So that's why the absolute values here, we say that the number on the inside, the x value, could have been positive or could have been negative. We don't know. And then the square root of 9 only returns 3. So then you can say, okay, so x, the thing on the inside, could have been positive 3 or negative 3. If you bring that up, I'm sure your teacher may be suitably impressed. Okay, so then, with all this stuff going on, if we do something a little more complex, we can do something like y equals 3 times x minus 4 squared minus 2. Okay, so this is another form of a quadratic. This particular one is in what we call vertex form, or on this channel we call it transformation form, because this has done a certain function transformation to a standard quadratic to become this particular thing. This is actually super easy to find the zeros and a bunch of other stuff. So I do like, and I like graphing particularly with this. So yeah, so if you take a general form quadratic and then do completing the square, you get back here. But one of the things that I do is I actually start with this with my students. 4 to the right, 2 down. So we're going to be like here. So if we count all of these as 2's, you may or may not like this, by the way. It's kind of a toss-up. Okay, so our standard function of any kind is going to look like y equals a times f of b times the quantity x minus c plus d. Again, you may not like this. We're kind of jumping into the middle of it. All right, a is a vertical stretch. B is a horizontal compression. C is a horizontal shift, where if you see a positive, this will shift left. And if you see a negative, it'll shift right. And D is a vertical shift, where again, if you see a positive, this is actually going to shift up. And if you see a negative, this is going to shift down. Okay, now, what we have here is a parent function f of x equals x squared. Then it has had these particular transformations done to it. So it has been multiplied on the outside, which is our a value. So it has been stretched vertically by a factor of 3. So all of its distances are now stretched by a factor of 3. The basic distances for a quadratic, I'm sure you know by now, are going to look like -3, -2, -1, 0, 1, 2, and 3 are going to be 9, 4, 1, 0, 1, 4, and 9. All right, I use this as a distance template. So rather than trying to figure out exactly where all of these things are on the graph, just to say here's x, here's y, I instead use this as a distance template. So what I will do is I will go over and see this has been shifted to the right 4 spaces and down 2, according to our stuff up here. So to the right 4 and down 2 puts our vertex, or what we can call the new origin point. So this is the origin point for this particular function. It's going to be at 4, 2. -2, damn. 4, -2. All right, so down here. Then, the thing that will establish the pattern is going to be our initial point. Our initial point is 1, 1 in the parent function. And again, the origin point in the parent function is just 0, 0. It is the origin. All right. The initial point establishes the pattern. Now, over here, normally we would take this and we would go over 1 and up 1. And then this would be our new point, our first point in the quadratic. So go like that. Instead, however, now we are going to go over 1, and it's been tripled in the vertical direction. Our a value is 3. So we're going to go up 1, 2, 3. And our new initial point is going to be here at 5, 1. Then, if we go over 2, normally we'd be going up 4, but now we're tripling that distance, and now it's going to be up 12. So 12 from 2 is going to be, damn, it's going to be 10. It's going to be too high. 6, 8, 10. Yeah, cool. So now we're all the way up there. On the opposite side, it does the same thing, but now it's going to be just mirrored. So we go over 1, up 3, over 2, up 12. I should have crunched this down a bit, but anyway. And now this is going to go up like this. Very charitable, thank you. It's supposed to be more vertical. Whatever. It worked. Goes like that. Okay. So this is one of my favorite things about graphing this particular stuff, is you can do all these fun sorts of little tweaks and just change it a little bit. All right, so now this also gives us a rough estimate of where our horizontal intercepts are going to be. So we know it's going to be a little bit more than 3 and a little bit less than 5. But our intercepts we can find by doing 0 for y is equal to 3 times the quantity, x minus 4, parentheses squared, minus 2. Then we add the 2 over to the other side. 3 parentheses 3, x minus 4 squared divided by 3. So 2/3 is equal to parentheses x minus 4 squared. Take the square root of both sides. Absolute value of x minus 4 is equal to the square root of 2 over 3. All right, with this, absolute value is going to create our number line. So how we do this is we say that x is our unknown value. That goes out here. 4 is our target value. That goes in the middle. How close are we to 4? Well, we are this far away. Square root of 2/3 up and square root of 2/3 down. So positive, negative. This one is going to get us then, again, because it's equal to, we have to find those exact locations. This one is going to be 4 minus the square root of 2/3. And then this one's going to be 4 plus the square root of 2/3. This offers a sort of graphical way to look at this without being like literally graphical like the one way over there. So it allows us to say, okay, x is going to be equal to 4 plus or minus square root of 2/3. And yeah, if your teacher insists on you rationalizing the denominator, you can do that. Yeah, and I solve all of my, it's weird. I solve all of my absolute values this way now. So all of them. It also helps the students not trip over the fact that, like, inequalities, you can have, like, have us go off to either side, and what the hell is going on? My phone is having a real hard time with the stream. It's weird. Anyway, so it allows us to do inequalities, and it makes it much more intuitive, I think. I'm going to actually publish a thing on this eventually, and hopefully somebody will like it. Okay. So here's the thing, right? This is all well and good. Does it work? Sure, if you have it in vertex form, or if you know where the vertex is. But if you have it in general form, so y equals ax squared plus bx plus c, then this presents a little bit of a challenge. Because, again, this is not quite as nice. Finding the zeros is not quite as nice. But if we were to multiply all of this out, right, so let's get y equals a times x minus c, parentheses squared plus d, right, and a b. And highlight a few things. So I do apologize, I'm not answering your original question, at least not yet. If you'll indulge me, we'll get there. If you need something a little quicker, we can just move along. Okay. Okay, so here, if we look at this, we've got this term which has b times parentheses x minus c all squared. Also, if you look at general form, we've got this ax squared plus bx plus c. You'll probably note that b and c here are not equivalent to the b and c there. So this creates a conflict. So we need to be able to change this to do something else and say, all right, we don't want to get these confused, so let's change it up and figure out what that's going to be. So one way that we can do this is say, we can simplify this a bit. Here, when we have the parentheses that are all squared, we can say that this is now going to be b squared times x minus c squared plus d. And now this part is just on the outside of the function. That's just like the original a. So this modifies our a value, and now it becomes like y equals a star, just a different a, times x minus c squared plus d. So if you ever have a b that's on the inside of a quadratic, you can square it and knock it out. Or you can keep it where it is. Sometimes I do like my particular graphing method, using a and b rather than using like a very large a value. So if it's like 32, I would take the 16, knock it inside as a 4. So it's 4 squared, which then can be pulled inside. And then the 2 can remain outside as a. That then does a horizontal compression as well as a vertical stretch. Does 2 things at once. So, up to you, it doesn't really matter. All right, then from here, we can look at this and say, all right, look, so this means that we have our vertex, which is at c comma d, which is also the new origin point. Just as we'd written it before. So then we want to get this also in terms of figuring out this one over here. And again, we'll change up the values here so that y is equal to, we'll let this be a again, just as a general a, times the quantity, x minus, now in this case, horizontal, h. So x minus h squared, horizontal value for the vertex, plus k, constant. That's really all it means. So now our new vertex point is just going to change letters and just be h comma k instead of c comma d. Because again, this would just cause confusion if we've got this other b and c up here. The general form is great for when you're talking about, hello? Okay. Very abrupt cutoff to that song. So, general form is great when you're just talking about generic polynomials, because you just keep extending a new term on every time. But it's not so great when you're talking about something specific like our vertex. So our vertex form or transformation form we use like this, and we'll, again, use a different letter for it. Okay, now if we want to multiply this out and get it into general form so that we can compare the two, we'll just eliminate that for the second. All right, this is going to be y equals a times the quantity, x minus h parentheses squared is going to be x squared. When we take our x from both of them and multiply them together. Our next term is going to be x times the negative h from the second one. So that's going to be a minus xh. The next one is going to be the negative h from the first one and the x from the second one. So that's going to be also a negative hx, whichever way you want to do it. And the last term is multiplying our two negative h's together to get positive h squared plus k. Bringing these together, we're going to get here an ax squared minus here we have a minus 2hx. So here this is going to be a minus 2ahx. And then here we have a plus ah squared and plus k. So now if we look at this in terms of the general form, we've got all the stuff here. Ax squared plus bx plus c. So b is all this here, and c is all this here. So we let set them equal to each other. I don't need to let. Don't need to do that today. Here, ax squared is just ax squared, so we don't change anything. There's no change in relationship here. Here, we've got that b is equal to a negative 2ah. And here, we've got that c is equal to ah squared plus k. Okay, we're trying to find h and k in terms of our general form ABC. So, sorry, got a message on Discord apparently. So here, we want to figure out what h is. That was just cough, but thank you. We've got here that h is going to be equal to a negative b over 2a. And here, we now know what h is in terms of the other stuff, so we're going to try to find k. So k is equal to c minus ah squared, where h is negative b over 2a, parentheses squared. This then makes c minus a times negative b all squared is just b squared over 2a parentheses squared is going to be 4a squared. Here we're multiplying an a, so if we multiply an a to the top, we can divide that out with one of the a's from the bottom. So k is equal to c minus b squared over 4a. This one should look familiar. This one, however, probably is not. I don't blame you if it doesn't. If it does, awesome. If it doesn't look particularly familiar, it's because we don't usually use this. 99.9% of the time when we say find the y value of the vertex, what we really mean is y equals a times plug in h. So we get negative b over 2a parentheses squared plus b times negative b over 2a. Wait a minute. Yeah, okay. Oof. And then plus c. And those all have numbers in them. And then instead of messing around with all this stuff, you're just plugging in numbers, and then you multiply all this out, you get the numbers, and then y is equal to some number. So again, this may be one of the first times you've ever seen this done in general, but this is kind of how I do things, so that students really get, like, this works for anything. Plug in any numbers you want. So, plug in h, which is again the x value, and simplify. Well, really it's evaluate. We're not simplifying. All right, so come up with a number, what this all boils down to. And also, I would never ask my students to like memorize this thing because it's just ridiculous. Um, random number. Okay, and yeah, we could probably even see it off of, you know, this thing up here. We've got a 4 and a -2, so we could do that if we had it in a multiplied out form as well. That'd be 1648. Uh, 48 minus b squared would have been 824. 24 squared. Ugh. Okay. Okay, that's getting too big. Let's too big to just quickly do in my head. At any rate, we get -2. Okay, now the important thing to go from here is we say, okay, if we want to find the x-intercepts, what we can do is take our original function, so y equals a times the quantity x minus h squared plus k, and say, all right, x-intercepts are where y is equal to 0. So eliminate that, make it 0. We get a -k is equal to a x minus h squared, like that, divide by a. -k over a is equal to parentheses x plus minus x minus h parentheses squared. Take the square root again. This is now going to be the absolute value of x minus h is equal to root -k over a, which again, number line makes h in the middle, and the distance is going to be the square root of -k over a. So whatever your vertex value, vertex's y value is, we negate it and divide by a, and then you take the square root of that thing. And that's what we get. All right, and in the opposite direction over here, this is going to be the square root of -k over a, but it's in the negative direction. And again, we get these particular locations. So again, our our x values are going to be equal to h plus or minus square root of -k over a. If you have this in vertex form, it's super easy to find these, and you don't even have to memorize it, because if you're looking at this, right, it was super easy with only a few moves to just move stuff over, take the square root eventually, and you get your absolute value. It gets you 2 possible answers. Et voila. If, again, you would like this in general form instead, we can go back to, here and say, okay, h, we already know, is -b over 2a, which again, you should know this, probably, -b over 2a for h. Then you get this plus or minus square root. -k is equal to all this stuff. Well, it's negative parentheses c minus b squared over 4a all over a. It's -b over 2a plus or minus square root -c plus b squared over 4a all over a. I don't like having compound fractions, so I'm going to multiply by 4a over 4a inside the square root. -b over 2a plus or minus big square root. This is going to be a negative 4ac plus b squared all over 4a squared. If you remember the 4a squared that we had up here, oops, negative 4a, the 4a squared that we had up here came from 2a parentheses squared. So we can do that as well. B over 2a plus or minus square root of the top, b squared minus 4ac, all over square root parentheses 2a squared. And finally, last step. Combine the fractions because the denominator here is just 2a. So x is equal to negative b plus or minus square root b squared minus 4ac, all divided by 2a. I love this derivation of the quadratic formula because it doesn't require completing the square. As long as you know what the vertex is, that's where it comes from. So you have your vertex form, you use the definitions of what your vertex pieces are going to be, and then it just falls out naturally. It's very nice. Anyway, so getting on to your previous question. What are imaginary numbers? So this is what happens when a bunch of mathematicians get together and decide we're not going to care about what really exists in mathematics, like the applications of math. Like, who cares about the applications? What we care about is what games you can play. So some mathematicians somewhere around the 1500s-ish noticed that when he was taking, well, I mean, it could have been earlier than that, but again, 1500s, Italy mostly was the central hub in Europe for being able to solve, quadratic equations, stuff like that. So what happened was they end up with something like 2 plus or minus the square root of negative 12 over 4. Now let's do 6 because I did this earlier. Oops. Over 6. They look at this and they say, okay, can't do anything. For the longest time, mathematicians in Europe just said, can't take a square root of a negative number, walk away. That's it. At some point, somebody said, well, hang on, I can factor this, and I can actually clean up the square root of 12. If this was just the square root of 12, we would do this and take out the 4. And do, this is equal to 2 plus or minus the square root of 4 times the square root of negative 3 divided by 6. And so they go 2 plus or minus 2 square roots of negative 3 all over 6. Oh, there's a common factor there. So we pull out a 2 from the top, and we leave 1 plus or minus 1 square root of negative 3 all over 2 times 3, which is 6. Get rid of the 2's top and bottom, and so our x values are now 1 plus or minus the square root of negative 3 all over 3. And then they satisfy themselves with this being the answer. So René Descartes comes around, looks at this, and says, all right, I don't know why you people are wasting your time on such imaginary numbers. And much to his irritation, the name stuck. So this is the imaginary component, whereas this other thing over here, the 1, specifically in this case, is going to be the real component. This is a little bit like when you have your RGB connection. Yeah. Yep. So this is a little bit like when you have your RGB connection on the back of your television, although these days it's all HDMI anyway. But the component portion is a red, a green, and a blue. And here, for complex numbers, what we have is a real component and an imaginary component. When you bring them together, it makes a complex number. Yeah. So we have... I'll do the chart later. We've spent enough time messing around with other stuff. So remind me, or I can remind myself here. We'll talk about real numbers and how to build them out. So in terms of the complex numbers, you've got this real component and imaginary component. The proper form for a complex number, we call them z, and it's equal to some a plus some b times I, where a and b both belong to the set of real numbers. And I is defined as the imaginary component, the square root of -1. So here we've got our a, our b, which are just any real number you want. And then I, which is the square root of -1, is only attached to the b. So now you've got your real component of z is going to be equal to a. Your imaginary component of z is going to be b. So if you ever want just those individual terms, this is actually a function you can use, real of z, imaginary of z, and it gets you just the numbers that are sitting in front of, well, a is just the number itself, b is the number that's sitting in front of I. Okay, so let's say you have just two imaginary numbers. So z1 is going to be equal to 1 minus 3i, and z2 is going to be equal to -5 minus 2i. Now I've just made these up on the spot. I don't know what's going to happen here. I don't know exactly what values these are all going to have, but what we know right now is the scheme. This is how this is. When you take your imaginary numbers, or sorry, when you take your complex numbers and you want to do operations with them, we have to fall back on all of the things that we learned about real numbers. My phone is my monitor. Like, I need to make sure that the stream's working right and all that, but my phone's not working right at this point, so it's just like, or rather, my Wi-Fi isn't working right at this point, so it's anyway. Okay, so what we would like to do is prove that the complex numbers constitute a field. So in mathematics, what you need to prove in order to prove that something constitutes a field is, at the very least, that there is an addition operation, that there is a multiplication operation, and there are some other properties, which include like identity and inverse. So each of the operations, addition and multiplication, need to have an additive and multiplicative identity and an additive and multiplicative inverse. Which also need to belong to the complex numbers. And again, remember that the complex numbers have to look like this. So we have to return everything that we do back to that form, a plus bi. Otherwise, it doesn't work. And we just say, oh, too bad. It's not a field. All right, so in what we call abstract algebra, this becomes a much more important thing, where we prove that something is a field and it has long-reaching consequences, because you can do stuff with a field that you can't do with other structures. So you can, take certain liberties for granted and be like, well, if it's a field, then we know that it can do this. Now, in terms of like pre-calc, we're not doing that. But I like to show my students just real quick, like, there's this thing. And we need to prove that all of these things exist, because otherwise, if the complex numbers don't constitute a field, we're going to have problems. Like, we're going to have some issues with it. We're not going to be able to do the things that we just do with real numbers and take things for granted. So, at any rate, we have addition. So, how does addition work? Well, if we do z1 plus z2, we get parentheses 1 minus 3i plus parentheses negative 5 minus 2i. Well, parentheses in this particular case don't really mean anything, so they're not holding anything back. So we'll just get rid of them. And then we can combine any like terms we have. So get the real portions together, get the imaginary portions together. So you would probably call this combine like terms. So here we can say that with regular addition of just regular real numbers, we have commutativity. So we can take this thing or we can reverse its order because that's how addition works. And if we just let I represent this imaginary number, the square root of negative 1, it follows the same rules as real numbers, even though it itself is not real. So whereas we might not be able to commute whole, like, complex numbers together all at once, we totally can. We might say, just for the moment, that we're going to commute the middle two numbers here and get a 1 plus a negative 5 plus a 3i plus a negative 3i plus a negative 2i. And again, parentheses don't particularly matter here. These just combine, right? Whole numbers. So 1 minus 5 is going to get us a negative 4. Then over here, we have to factor out that I. Again, we treat it as though it is a real number, or just a variable, basically. And we can let I be factored out, and then on the inside, we get a negative 3 plus a negative 2, which is then a negative 5. So negative 4 minus 5i. A is negative 4, B is negative 5. Now we've just proven that z1 plus z2 will come out with some nice value, which is itself a complex number up above. Okay, so addition's working. Good. Now this, granted, only means that it works for these two numbers. If you want to prove it in general, you do have to say, okay, z1 plus z2 is equal to a1 plus b1i plus a2 plus b2i. But it does the same thing, right? Everything that we did up there with the numbers, we can do down here with the, unknown constants. And so we end up getting a1 plus a2 as the real component, plus parentheses b1 plus b2 all times I as our imaginary component. So this is our z1 plus z2, and we know that in general, this is going to be the case. Whenever we want to add two complex numbers together, we just need to combine like terms. Take the real portion, take the imaginary portion, separate them, add them separately. Easy enough. Okay, then we have to do z1 times z2, and again, we can do an example first to see what's going to happen. So this is 1 minus 3i multiplied by negative 5 minus 2i. And again, standard notion of multiplication. All of this, we can say, like, the individual things are going to be real numbers, with the exception of the I, which again we treat like a variable. So when we multiply all this stuff out, we get a 1 times negative 5. It's going to be negative 5. A 1 times negative 2i is a negative 2i. A negative 3i times a negative 5 is going to be a positive 15i. And a negative 3i times a negative 2i is going to be a positive 6i squared. This is the first time that we've run into this. this I squared thing? Well, we know that I is just the square root of negative 1. So if I is equal to the square root of negative 1, then I squared is equal to the square root of negative 1 parentheses squared. Which means that, again, the square and the square root undo each other, and we get a negative 1. I think you meant to hit that. But all right, so I squared is going to be a negative 1. Okay, so then here we say that's going to be a negative 5. We bring this over here. This is going to be a minus 6. So now, notice that this has become a real number. So our I squared has become a real number. Huh. All right, and then over here we get our two i's. And again, same deal, factor out the I. And then the rest of it is a plus parentheses negative 2 plus 15, or 13i. 13i, positive 13i with a negative 11. So this is what happens when we multiply z1 and z2. So it seems straightforward enough. Albeit it's a little work, but yeah, it's not too bad. Again, if we do it in general, it becomes a little bit harder. But same deal. So this is a1 plus b1i multiplied by a2 plus b2i. We multiply a1, a2 and get a real number. We multiply b1i and b2i and we also get a real number. So remember that this is going to be now a plus b1, b2 I squared, which we'll deal with that on the next step. Then we end up with a plus a1, b2i. Yes. Sort of. That you need to know about? Yes. I'm very hesitant. Okay, and an A2 B1I here. So, right, end of the semester. What kind of pre-calc are you in? Is this going to also include trig, or is this going to just be like function analysis? So A1, A2 minus B1, B2 pre-function. Okay. Plus parentheses A1, B2 plus A2, B1, I. All right, so that is the actual, like, multiplied out version of what you will get every single time that you do it. Okay. Just extend that a little bit further. Cool. All right, that is like an extended version of what you will get every single time that you multiply two complex numbers together. All right, and you know what their what's called rectangular form is going to be. So this stuff, when you have the multiplied out versions of Z1 and Z2, that's what you're going to get. Now, again, would I want my students to memorize this stuff? Absolutely not. But I do want them to recognize the structure. Because if you look at it, right, you multiply together your real components and you subtract, you're adding in some sense, the imaginary components, right? So it's the product of the reals minus the product of the imaginaries. Well, that's kind of interesting. And then over here are cross terms The A1, B2, and A2, B1 are what happens when you multiply reals by imaginaries. And those become imaginary at the end. So I find that kind of fascinating, like, well, that's a little weird. And it comes back later when you're dealing with vectors. All of this stuff comes back when you're dealing with vectors. It's crazy. It's absolutely amazing. All right. So then when you look at, is this a field? The other thing is, do we have some sort of identity? In this case, this is going to be additive identity. And then do we have an additive inverse? So just looking at it, you can say, yes, we do. An additive identity is the thing that you're going to take some z, and you're going to add the identity to it, and you're going to get z back. Okay, well, again, if this acts like real numbers, then we have a plus bi plus, and this is our identity stuff. So like a of the identity plus b of the identity times I has to be equal to a plus bi, the original one. Well, okay. Again, at this point it becomes trivial and silly because we're saying, okay, you're just adding the real components together and the imaginary components together, just like we did for addition, right? Yes. But when you get to like abstract algebra, you have to actually prove this stuff and say, oh, well, you can't just take things for granted. You have to say, here, this is a plus a identity has to be equal to a, and b plus b identity has to be equal to b in the real numbers. Because all of the individual components are real numbers. All right, and technically, I mean, this is really where we get this stuff, like the b1 plus b2 parentheses I. You have to use the those things that we had up here, the real of and imaginary of, to do all this stuff. We're not doing formal proofs. Like, this is ridiculous. We don't want to do that. So here, what we say is, well, I know what this is in the real numbers. The identity is just 0. It's a plus 0 equals a, and b plus 0 equals b. So here you say, okay, well, a sub I has to be 0, and b sub I has to be 0. So therefore, a sub I plus b sub I times square root of negative 1 has to be equal to 0 plus 0i. Well, there we go. So now we've proven that the identity has to be 0 plus 0i. And then the additive inverse. Well, it's the same thing. The additive inverse says that a plus, well, okay, start with z. Right, z plus the inverse, and sure, is equal to the identity from up above. Well, now this says that z plus this inverse has to be 0 plus 0i. Okay, z has to be a plus bi. And then n, our inverse, has to be a sub n plus b sub n times I. same deal again. This has to be b plus bn is equal to 0 for I. And also a plus a sub n has to be equal to 0 for the real component. Again, we know what this is. It's just going to be the negative of this stuff. A sub n is equal to negative a, and b sub n is equal to negative b. And so n has to be equal to negative a minus bi. So again, we prove that these things exist. All right, then we could do all the same for the multiplicative stuff too. Multiplicative identity, no surprise here, is going to be 1. The number that you multiply by to get the same number back. It's just 1. But it works even for complex numbers. So that's something that some people find a little bit strange, is that shouldn't it be like 1 plus some number of i's? Like 1 plus 1i? Or something else? And the answer is no. The I term actually does something completely different. If you multiply by an I, it's going to make your reals become imaginary, and your imaginaries become real. So it's going to like take these things and change their values. So it can't be something with I. It's got to be pure real, and we find it's just 1. All right, so then you've got to do the same thing with the inverse, which again, you look at it and you say, okay, we're saying z times some multiplicative inverse has to be equal to the multiplicative identity, which was 1. Well, we know in real numbers that this should be 1 over z, 1 over the thing we just had. But here we can't take that for granted. So we've got to say this is a plus bi multiplied by something else, right? A sub m plus b sub mi, which has to be equal to 1. So now we have to take this and multiply it through. So a times am. And remember, we're doing the same thing as the multiplication that we had right over here. So that's a times am minus, because again, plus b times bm times I squared. So that gets the negative 1 out front. Then we've got the cross terms, plus parentheses abm plus amb times I has to be equal to 1, and that's 1 plus 0i, by the way, right? So then here we see that am minus bm has got to be equal to 1. Whereas at the same time, abm plus amb has got to be equal to 0. This is really weird. So this becomes really difficult to try to parse beyond this point. I'm not going to... I can go one more step. All right, so if we do this, we're going to say we want to solve for a sub m. So get this a sub m by itself. So move this over. A sub m is going to be equal to negative a b sub m over b. And then we want to take all this and plug it into there. It's a little ridiculous. But we basically say that we know what a and b are going to be, and we need to find what a sub m and b sub m are. All right, one sec. Let me put on something for just a minute here. And yeah, be right back. Okay, so I just wanted to make sure we got the pre-roll ads off for anybody who's coming in. So that'll at least work for the next 20 minutes. All right, so this is the sort of thing that mathematicians do. It ends up being somewhat difficult just to try to make all of this work. But it can be it can be very rewarding just as like a big puzzle. You want to, do some interesting things. Like I said, sometimes it gets a little ridiculous in the, size and scope of all this stuff, but, I find it really rewarding. And like, I really like puzzles, so that's probably why I like this, and being able to like, go hunt for the multiplicative inverse of this. So this is why I really liked abstract algebra when I took it. You opened it, now all the ills are out in the world. All right, so eventually this all works out so that our a sub m can be equal to some sort of particular expression, and our b sub m is going to work out to some particular expression. Again, I'm not going to work it out here with this stuff, but I will show you an easier way. So if we assume that real numbers and complex numbers work the same sort of way, not exactly the same, but the same sort of way, then z can be multiplied by 1 over z to get us just 1. Plain 1. And they do in fact work this way, but you have to prove it first in order to really do it. And again, that's why all of this kind of works. But so what we do is we say, okay, this is going to be a plus bi, and then we're going to divide by a plus bi, and we're kind of assuming that this is going to be equal to 1. But again, you can't really do that. So what we have to do instead is say, well, look at this thing. This is now... Actually, right, we still don't technically know if this is going to work. So what we have to do is look at 1 over z and say, is 1 over z just going to be 1 over a plus bi? All right, we want it to work out this way, but we can't know it yet. So what we have to do is we say we need to get rid of the I that's in the denominator. We have to split this up into a real component and an imaginary component. So you can't split denominators. That's a big no-no, right? You can't split the denominator. You can only split a numerator, and then the denominator gets given to both portions. So here we've got to get rid of the I that's in the denominator. Well, you can get rid of the I the same way that you could get rid of a square root that's in the denominator, because it is a square root. You have to multiply by that particular number in a certain arrangement in order to square that term. So if we just multiply by I, we get an I squared. So it's -1. Oh, good. But then it also multiplies the A by I, and so it becomes imaginary again. And it just shifts where the imaginary portion is. So that's not it. I've had my students say, well, what if we just square the whole number on the bottom? Okay, but if you multiply a number by itself, remember what happens. You get your, you'd have your a squared, you'd have your b squared, and then you'd have your cross terms. So your a times b and your b times a is going to form again, and then that gets our I term. So you can't square the number. Okay, but then somebody remembered, there's this thing, a plus b times a minus b is going to get us a squared minus b squared, which squares the terms and gets rid of the cross terms. So a squared minus ab plus ab minus b squared. So that is exactly what we want here, is if you just switch the sign of the I portion, the imaginary portion, and multiply both top and bottom by a minus bi. This is what's known as the complex conjugate. So if z is a plus bi, then the complex conjugate is going to be z bar a minus bi. When you multiply these things together, the top, again, now becomes 1 times a minus bi. The bottom becomes a squared. All right, a times negative bi and a times positive bi. The middle terms are gone again. So now we have no imaginary portion. And then bi times negative bi is a negative b squared I squared, which the I squared becomes negative 1, multiplies the negative that was already out front, and now becomes a squared plus b squared. So if you remember hearing ever your teachers say, well, you can't factor a sum of two squares, they were partially right. You can't factor the sum of two squares with real numbers. You'd have to use imaginary components. So you'd have to have the complex conjugate to multiply those together and get the sum of squares to be able to be factored. Okay, so now we look at this and say, does this follow the same rules? Does this now follow the same rules as all of our other stuff up there? Can it be turned into a plus bi? Now in this case, it's not literally a and b. It's going to be instead a over a squared plus b squared, which is a real number, minus b over a squared plus b squared, which is a real number, times I. So a plus bi. So this whole thing here is the a, and this whole thing here is the b. So now our reciprocal, our 1 over z, our multiplicative inverse, is this thing. It's pretty big and it's pretty ugly, but nonetheless. So this is 1 over z. That's our multiplicative inverse of a plus bi. And again, this thing crops up yet again in vectors. If we look at it and think of complex numbers as a vector, right? It's going to start from 0, 0, and then it's going to go out to a certain place. If that certain place is, for instance, that's totally this point here. You just make it bigger, nobody will notice. Right, this is the vector 1, 2. Well, this could also be 1 plus 2i. What's the length of that vector? Well, it's 2 in this direction, it's 1 in this direction, and it's at a right angle. Seen it yet? Right, the length of 1 plus 2i, the absolute value of 1 plus 2i, the distance that this thing is from 0. The absolute value is the distance from 0. So the absolute value of 1 plus 2i is the distance that this vector is from 0. It gets us a Pythagorean triangle. 1 squared plus 2 squared is going to end up being square root of 5. So the absolute value of 1 plus 2i is equal to the square root of 1 squared plus 2 squared. Again, square root of 5. And then the multiplicative inverse of this particular number is then, therefore, going to be, so 1 over 1 plus 2i is going to be equal to, our a term is going to be our original a, which is 1, divided by a squared plus b squared is 5. So 1/5. We get a negative b, which b was 2, so now it's going to be negative 2 over the same value, 5, 2/5 I. And if you want to check it, right, you just check it versus 1 plus 2i by multiplying them together. So I really hope this works. It should, right? The math works out. Unless I really screwed up. Minus 2/5 I. Okay, so this is going to be 1 times 1/5 is going to be 1/5. 1 times a negative 2/5 I. 2i times 1/5 is going to be a positive 2/5 I. Oh, look at that. They divide out, or they add to 0, whatever it was. And then 2i times negative 2/5 I. This is going to end up being a negative 4/5 I squared. I squared is again negative 1. Negative 1 times 4/5 is going to be 1/5 plus 4/5 plus 0i. Oh, would you look at that? It worked out. 1/5 plus 4/5 is 1 plus 0i. Right, so it looks all complicated and stuff like that, but at its heart, it really isn't that bad. It's just a matter of understanding like the relationship that exists that's there. My mother was not a mathematically minded type person, but you know, she kind of appreciated mathematics and eventually really got into her stride in statistics because she was in healthcare for a really long time and still is to this day. So she's a school nurse up in New Hampshire, and where we're originally from, and so has been back when she was in college, she would come home to a roommate who was absolutely obsessed with soap operas, and she was just like, "Oh my God, I can't believe she's watching that again." And so she would, she was told at some point that, you know, mathematics is all about relationships and figuring out the relationships that exist between the numbers, the types of numbers, and what operations we're using and all that stuff. And her roommate was notoriously awful at mathematics, and she was just like, now hang on a second. This girl can keep track of like 40 different characters on screen and all of their ridiculous relationships that they've got between each other, but she can't figure out how to work mathematics. I always found it amusing when she brought out that story. It's like, Mom, how come you weren't better at math? And she was like, yeah, you kind of have to be invested in understanding, like, again, I really like the puzzle aspect of it. And so it's you know, trying to find this thing to work out exactly how this is going to work. Which, by the way, if we take this thing right here, we can notice that it actually does pop out. Yeah, this one right here today. Where was it? This one right here. I seriously popped some skulls today. I just saw it in like 5 different students. They were like, I'm like, hey, yep. Because they saw me bring these two things together and then put this on the board, and then they said, we're solving for H, and I was like, yep. H is the vertex. Yep. Anyway, with this one up here, right, I had said, oh, well, let's not worry about this yet. So, if we do it now, this is going to be A times negative A BM over B minus BBM equals 1. Now, what we want here is to solve for AM and BM. AM's gone for the moment, so we'll solve for BM. This is going to make negative A squared BM over B minus BBM equals 1. We can factor out a BM from both terms. Nope, factor, not equal. Factor out from both terms, and we leave behind an A squared over B minus B, parentheses, all equals 1. Right, again, you may not see quite where this is going yet, but if we multiply both sides by B, we get rid of this fraction. I should have done it on the previous step, but whatever, it's fine. This is going to be BM times the quantity, negative A squared, minus, now this becomes B squared, equals B. See it yet? BM is going to be equal to, again, remember this is the inverse 1 over Z, essentially, of just the B term. What that's going to be, this is B. We divide by, this is a real number. Divide by the real number. Divided by a negative parentheses, A squared plus B squared. We've seen that before. It's right here. Negative B divided by A squared plus B squared. Well, having a negative on the bottom or having a negative out front or having a negative on top, it's all the same stuff. So that, we finally get it. And now we could do the same thing with AM. So if AM is equal to this stuff, AM is equal to negative A BM over B, well, let's fiddle a little bit here. This is going to be negative A over B times BM, which is what we just found up above. So negative B over A squared plus B squared. Well, now this is B divided by B. We got a negative here and a negative here, so those are gone. So now AM is equal to A over A squared plus B squared. That's what we got right there. All of it fits together. It's a really awesome jigsaw puzzle. So we could have gone through it in a more abstract manner, like this stuff up here. But it was a little bit hard at that exact moment to, see through all these A's and B's and B sub M and A sub M. It was a little mean of me to use stuff with subscripts that match the same letter as the other stuff. But, again, it allows us, I think, to really understand, like, what does this stand for? What does it really mean, this thing? So if you put it all together, all these pieces, and you can start understanding what the relationships are between them and how it all fits together. All right, so your eyes. You might be able to clip it still. Um, uh, that's a very good question. Incoming raid! Vainglorious Gaming. Hey, how's it going? Everybody, raiders, welcome in. I am Obi-Wan Pez. This is N-Simplex Pachinko, my home for all this awesome mathematical stuff. Today, we've been working on complex numbers. So, everybody might say, but all numbers are complex. No, no, no. Real complex numbers. So anyway, we've been talking about the square root of -1, specifically I, and how all this crazy stuff works. Brandon, what are you up to? And a shout out for Vainglorious Gaming. Brandon was playing Timberborn tonight. Lovely. I'd make a joke, but it might come off as wrong. Anyway. So yeah. I did want to play Timberborn. It's been a little bit. Is it I'll look it up later, but I was gonna ask if it's on Game Pass, but whatever. At any rate, how you been? Things here have been kind of crazy. So tonight, we're talking about complex numbers, specifically, again, square root of -1i. Just I. And how then all of this stuff works. So I've been trying to get our friend here, 26 Stacks, a little bit more familiar with the crazy field properties of complex numbers, which is well beyond what is necessary for that particular class. But you know what? The more we explore, the more interesting it becomes. I hope. So when you have I being the square root of -1, we're going to say that over here we've got I, which is going to be I to the first. If we then multiply by I, we're going to get an I squared. Now we already figured out up there that I squared is just equal to -1. So we square a square root, it undoes it, and just the stuff on the inside's left over. Okay, so then if we multiply by yet another I after that, we get I to the third, which is going to be equal to I squared times another I. So now we take I squared, which is -1, and multiply by I, we get a negative I. Okay, and we take I to the third and multiply by another I, we get I to the fourth. And so that takes our stuff above -I and multiplies it by I again. So we see that this is going to be negative I squared. Well, I squared is -1, so negative -1 is just going to become 1. And then I to the fifth is going to be 1 times I is just I. I to the sixth is going to be I times I again is I squared, which is -1. And then I to the seventh, and I think you can see where this is going. Take that, multiply by I again, so -I. And I to the eighth is equal to, and here you could actually go all the way up to I to the fourth and say that I to the eighth is actually I to the fourth squared, which is just 1 squared, which is just 1. So I think you could probably see at this point, this is making a repeating pattern. And if there's one thing in math that we like, it's repeating patterns. And 26x, I don't mean to I didn't mean to sort of ignore your previous question, we had a raid, right? Can you repeat the quote that I said about relationships that exist in mathematics? The answer to that is probably no. My attention span is about yay long. But again, you can, well, can't clip it now anymore. I will go back. You know what? Let me it's about 140, somewhere around 140. ish. I'll keep a note for myself. I'm gonna try to go back after and find a clip of it. So go rummaging through my clips later, and we should be able to find it. But in essence, right, it's what all of the stuff is about. It's all relationships. And trying to figure out the relationships that exist within mathematics is the goal. Yeah. Oh, that's also a good question. Was that actually when I said the thing, or was it like 20 minutes ago? Oh well, I'll watch it. I got nothing better to do. Ayo. Alright, so here's the thing. Because we have this repeating pattern, we can actually rearrange it in something that looks like this. So we get I squared is -1. I to the third was -I. And I to the fourth was 1. So, as we multiply by I, as we go around, we're multiplying by I every single time. This creates what is called a 4 cycle. Now, cycles, and trying to understand cycles and trying to figure out like the properties of cycles and things like that, this goes yet again to abstract algebra. So you do not need to worry about this particular thing. But it is a helpful hint to be able to run things through faster in your head and just be like, what's really the important thing? Right? What's really important? So, in this cycle, as we multiply by I over and over and over again, we end up at one of these 4 results. Either I, -1, -I, or I. And so it keeps bouncing around like this over and over and over. So the question becomes, what would I to the 535th be? Now, if I were to just look at this, my first reaction would be, I don't know. My second reaction would be, oh, actually, yes, I do. Right? I know what's relevant and what isn't. So what's relevant to me is these last 2 numbers. Because this is a 4 cycle, I don't really care how many times I go around the thing. I don't care at all. What I care about is where I end up. So, what we really want to know is how many partial cycles do we go through? So not how many cycles, but how many partial cycles. Can you explain physics freefall problem? Yes-ish. If we're talking about in a vacuum, definitely. If we're talking about in an area with air resistance, then yes, but then it's going to require differential equations. Also, Blainland, how you doing? So when we take this number here, we're going to say I raised to the 6,535th power. We don't need to know how many total times it goes around. So how many times does this number result in a full cycle? Vector calc, yeah. Yeah, they do be making it somewhat difficult sometimes. So as we go around, you'll notice that as we reach this top point here, this is I to the 8th, I to the 12th, I to the 16th, etc. This is all multiples of 4. So if we were to take this number, 6,535, and divide by the size of the cycle, it's a 4 cycle, divide by the size of the cycle, we end up getting 1, or 1,000 total revolutions. All right, and minus 4 is going to get you a 2. And you know what? Let me... I'm going to go like this. This might freak some of you out. It's okay. I'm going to take my remainder and I'm going to stick it up there. Yes, raisins. How's it going? So here we take, this is now going to be 4 into 25 is going to go 6 times, which gets us a 24, which the remainder is going to be 1. 4 into 13 is going to go 3 times, which gets us 12 with a remainder of 1. And 4 into 15 is going to also go 3 times, this time with a remainder of 3. That gives us 12. So we get 15 minus 12 gets us 3. This whole bit here, the 1633, is how many times it goes around a full cycle. Who cares? Doesn't matter. Algebraically, I to the 6,000... Oh, it's behind my head. I do that all the time. I to the 6,535th power. Honestly, it's the same either way. Whether the hundreds was 300 or 500, doesn't matter. Is going to be equal to I to the 4th raised to the 1633rd power times an extra I to the 3rd. I to the 4th to the 1633rd is just 1 times I to the 3rd, which is equal to negative I. So we could do something with an insanely high power, like I to the 6,535th power, in mere seconds. I know that in order to be divisible by 4, you just have to look at the last 2 numbers. 35 is not divisible by 4, but 36 is, and 32 is. 32 plus 3 more is going to get you 35. So 32 would be our full cycles, and then 35 is 3 more. So we'd have 3 extras left over. It's I to the 3rd. Seconds. Yep. And you can even do that with the other one too. If you go the other way, if you go I to the negative 5,626th. Okay, same deal. If we go like this, and we go with a negative number, you could do this one of 2 ways. Either, I often recommend this, 1 over I to the positive 5,626th power. Easy enough. If it ends up with i's at the end, you do have to rationalize your denominator. But good news in this particular case, it won't, because it's an even value, so the even values only come out with 1 or negative 1. So in this particular case, we're going to say that this is going to be equal to 1 over I to the 4th raised to some number multiplied by I raised to some other number, again, remainder. So the value here, again, is going to be 5626 divided by 4. It's not going to be evenly divisible, so it is going to be negative 1. Just instantaneously, no, it's negative 1. But to check, just in case your teacher actually wants you to do some work, 4 into 5 goes once, with a remainder of 1. 4 into 16 goes 4 with a remainder of 0. 4 into 0, 2, or just 2, is 0. and then 4 into, with a remainder of 2, so it's just 26. 4 into 26 goes 6 times with a remainder of 2. So I to the 4th to the 1406th power times I squared. So now this is 1 over 1 times negative 1, which is just 1 over negative 1, which is just negative 1. All right, now I did say that that was one possible method of doing it. The other way that I like doing it is just saying, what do you get if you just do this? So we would have gotten I to the 4th raised to, right here, we've got it. It's a negative 1406 power multiplied by I to the negative 2nd power. It's just negative values. Raisins, thank you for the follow. We have a grand total of 1 emote. So feel free to use that in our chat here. Or oh. I hope that isn't... I don't think it's sub only. I need to check that later. I mean, you probably can figure it out from here, but stuff. Okay, so then here what we've got is negative 1406 with a negative 2 remainder. Yeah. Well, thank you very much for coming, and hope to see you again. We do math nights on Tuesday nights, usually 9 o'clock until whenever. Usually whenever I run out of coffee and or steam. Occasionally I will play a probably math-oriented game on Tuesday nights, unless we have an emergency inside of, say, like Elite Dangerous or something else that I really absolutely love, in which case I might go for it. Vintage Luigi, thank you very much for the bits. Had to try being first, yeah. Okay. And thank you for the follow. Yeah, so most of the time I'm doing math on Tuesday nights, and I will do games nights on Friday nights, just because I need some time to unwind after a long week. Occasionally people will still ask me mathy questions on Fridays, and I will be happy to pull up the whiteboard here and write out anything that needs to be done. So feel free and ask questions if you have any questions on mathy type stuff. I teach at a 2-year college on the eastern seaboard of the United States, and teach everything from like basic algebra all the way through differential equations. I myself have a master's degree in applied and computational mathematics, and can answer questions through like math analysis and stuff like that, but I'm not super great once we get outside of like what I've actually taught. I've done some stuff, but not a whole lot. And I'm trying to figure out tensor calculus, but that's going to be a really long road. So occasionally I will pull up Dr. Pavel Grinfeld's tensor calculus book and try to work on a little bit. It kind of sometimes works. Applied calculus, very nice 26 stacks. Yeah, if you get through your... I see. So this is probably what I would call business calc, or what it is at my school. Yeah, okay, I get it now. So the applied calc only requires that first part of pre-calc. Yeah, I gotcha. All right, this thing here, that's still 1. And this thing here, that's still going to be 1 over negative 1. Which in this case, again, it's just still negative 1. So we corroborate that this actually works in both directions. The challenge is when it's an odd value. So usually I almost always put odd values in my work in my class as well as on exams. It just becomes more interesting. Right, and it also makes sure that students understand that, you know, when you get to this point, you need to remember to rationalize the denominator, get your complex, or get your imaginary numbers out of the denominator. Yeah, partial differential equations. I've got a Shams book on that one, and a few like Dover books, and yeah, I took partial differential equations in my, well, Masters 2 stuff. And it was a lot of fun, but yeah, that was a lot of hard work. And it was like just pushing past where I was anywhere near comfortable doing, which is good for me. So, 1,000 Cranes, how you doing? Hope you're having a good evening. Some itchy eyes. I don't think I got anything in there, but I'm on allergy meds, so who knows? All right. So all this stuff is going to be how our complex numbers work with, you know, higher order powers and doing. We had done all this stuff earlier to prove that complex numbers form a field. Now I may actually have to do a few more things to prove it's a field, but you know, we got the basics down, so I'm gonna call it good. It's been a long time. So we're gonna move to, oh, right, complex numbers. So as a whole, our complex numbers stem out from our real numbers, which is all done by, or it was started by. Oy, cross product. Yes, and give me a few minutes because I'm going to need to look that one up. Cross product. I'm totally not just pulling up Wikipedia. That's fine. So we have what Cantor called the natural numbers, which were the numbers that most Europeans were working with back to the 1500s. This is what we were talking about before. So if you start counting, these are the counting numbers. So 1, 2, 3, etc. All right. Outside of that, Cantor had what he called the Zahlen, or set notation was a doubled Z. This was, Zahlen just basically means numbers or whole numbers in German. So in English, we call them integers. This includes everything. -3, -2, -1, 0, 1, 2, 3, etc. in both directions. And outside of Zahlen, then you have the, I don't remember what the German word is here, but it's the quotient values. So these are what are called rational numbers. The rational numbers are the first time you have to describe what the set is rather than being able to list them out. So here he said this was just something that looks like A divided by B, where A and B are going to be any integers that you want, with the exception that B cannot be 0. All right, fair enough. Oh well, sorry, Cantor. All right, and then outside of the rational numbers, we have what are called the algebraic numbers. And these are solutions to polynomials with rational coefficients. Now, in all reality, rational coefficients are identical to having integer coefficients. You just clear all of the fractions. So it doesn't really matter which way you put it, but so algebraic numbers include stuff like the square root of 2, phi, which is 1 plus the square root of 5 all over 2. It includes all sorts of other numbers. The fifth root of 1 plus the cube root of 7 inside of it. All sorts of stuff. So these are irrational, and they belong to this particular set. There are other irrational numbers. And specifically, there we go. Thank you for correcting me, whiteboard. These, so just the ones that belong to this ribbon here. Now keep in mind, algebraic numbers include everything in from there. Algebraic numbers are the set that includes all the subsets. The one that's out here is just this one here. This, like the set of all of it, is called the reals. This is where that term comes from. So the real numbers are everything from that outside circle in. So real numbers are all of this stuff. The outside ribbon alone is called the transcendental numbers. Or the transcendental reals. These are numbers which cannot possibly be described by any other of the other stuff. So you can't describe them as algebraic because they can't be solutions to polynomials whose coefficients are rational numbers. Stuff like pi, stuff like e, stuff like 0.10100100001, and so on. So these things they can have patterns, or it could just be even just random numbers like 0.5781238801112. Just kind of random digits that go on forever. It isn't any particular value. It's just something different. Yeah, they have to be infinite in extent, but they also can't match up with like one of these square root things, right? So like there could be a square root that gets really close to this, but basically we just say that it isn't that one. It's just slightly different. Who knows where? It's just different. So the transcendental reals are this thin ribbon that run around the outside of it. And then the last thing that happens is all of this stuff is mirrored over this line, where all we do is we take the real numbers, which has this sign with the doubled R. And again, that's all of them belong to the reals. You take this double R, or like, you know, your number, which belongs to the reals, and just multiply it by I. So this gets us the imaginaries. And then, when we take all of it together, this is where we get our complex numbers. which are, again, z a plus bi, where a and b are any real number you want, and I is the square root of -1. That one has a field notation C, doubled C. Set notation, sorry, not field notation, set notation. So all of this stuff is real numbers, regardless of whether it's on the imaginary side or the real side. It's just that when it's on the imaginary side, it's also multiplied by the square root of -1. It's the only difference. So all this creates this giant picture, and Cantor came up with all of this stuff. He eventually figured out, like, that there were different kinds of infinities by saying, well, the natural numbers can be put into a one-to-one correspondence with all these other sets, and then try to describe how to make that happen, or not make it happen. We could talk a little bit about that later. I do want to get to Blaine-Lynn's question. Can we do cross product? So, yes. Asterisk. It's been a long time. All right, so it is a directed area product. So if we have the vector, which runs out to here, and some other vector which runs out to here, we want to know what the angle is between them. Okay, if we are going from vector A here to vector B here, that's not it. Sorry, not a hat. Arrow. Vector A here to vector B here. Then A cross B is going to say that we want the size of the vector, which is going to represent a three-dimensional vector, A cross B, which is going to correspond with the right-hand rule. So essentially, this thing, the way I've drawn it, if the A and B are vectors on just the plane of the board, then A cross B is coming out toward me, because my right hand is going to wrap from A to B. Sorry, that's this way for you. And it's going to come out toward me. All right, then if I think of this as a three-dimensional space, and A and B are on a flat plane, and A cross B is going up like this, that might help. All right, to get the size, or to get the actual value of A cross B, then what we need to do is take the normal. Nope, that's not the normal. Take the size of A, multiply it by the size of B, and multiply it by the sine of theta times the normal vector. So the normal vector is going to get us just which direction is this going in. So most of the time, our normal vector is going to be C. All right, 26 stacks. Have a good night, if you're still here. If not, possibly see you on video on demand. All right, so the size of A is going to be determined by what your actual values are. So if we do this in terms of x comma y, or x hat, y hat, right? So let's let a vector be equal to, ew, that was kind of cool, but 3x hat plus minus 1 y hat. All right, let's try to make that approximately there. All right, b vector is going to be equal to 2, nope, other way. All right, approximately 1x hat plus 2y hat. All right, so let's just make it this stuff. Use easy numbers, all that. So the size of A is going to be the square root of 3 squared plus -1 squared, which is going to be equal to the square root of 10. All right, so we want the scalar that is the size of this vector. So 3 squared gets us, well, right, we're just doing Pythagorean theorem here at this point. Boop. So we go down this way and over that way. And again, this is going to be 3 and -1, and we just do Pythagorean stuff. Here, same deal. This is going to be a 2 versus a 1. Same deal there. So the b size is going to be equal to square root of 2 squared plus 1 squared. So that is going to be square root of 5. So then we've got a times b, size of a times size of b. So that's going to be root 10 times root 5 is going to be 5 root 2 times the sine of our angle, which let's have it be 60 degrees just to make it easy. Let theta be 60. Oh, wait, we have numbers. No, don't do that. Don't just let it be something. Idiot. We have numbers. All right. God. Oh, man. Okay. So the way that we're going to do this is we're going to say find the angles for each of these individual things and then find the difference between those two angles. So we're starting from A and moving to B. So that means that we're doing theta of B minus theta at A, because we're going in that particular direction. Because otherwise, remember, this would be like theta of B minus 0 if we started at 0. So that's what we want. If this were starting from 0 and going out to B, then we get theta of B minus 0. So just as a reminder, right? That's how we want to make this work. So theta of B is, we've got the tangent of theta sub B is going to be equal to the tangent of this stuff, which if you remember is going to be opposite over adjacent, or your y's over your x's. So that's going to be 2 over 1, which is also the slope, right? So the slope of this particular vector is 2 over 1. And so theta b is going to be inverse tangent of 2. And then tangent of theta sub a is going to be equal to, same deal here, 3 negative 1 is going to be a -1 over 3. So our theta sub a is going to be the inverse tangent of negative 1/3. So then theta b minus theta a is going to be equal to the inverse tangent of 2 minus the inverse tangent of negative 1/3. Inverse tangent is an odd function, so that negative on the inside can be kicked out, which is then going to make that a positive or plus. So inverse tangent of 2 plus inverse tangent of 1/3. So that stuff goes into here, into our sine function. Now you could figure out what the degrees are for that and figure it out. I don't like doing it because if it's off by a little bit, it's going to be off by a lot eventually. So the sine of parentheses tangent inverse of 2 plus tangent inverse of 1/3. Other option, you could also create a right triangle between these two vectors using this as your angle here. So drop a normal here, or drop an altitude to A. Drop an altitude to A, and then figure out what the relationship is there between your theta and the altitude you just dropped, which is now going to be like, not skew, but it's going to be, you know, some angle off from all the rest of the stuff. So it's going to be a little gross if you try to do it, but it's doable. Just don't know why you'd want to. All right, and in this case, our normal vector is going to be, if we're using x and y, our normal vector is going to be the z vector. So z hat. 3 left seconds. How's it going? My name is Obi-Wan Pez. This is N Simplex Pachinko. We are working on some math. If you have any questions, go ahead and drop it in chat. We're working on some vector stuff at the moment. We talked about complex numbers earlier in great detail. Well, that depends. My specialty tends to start running out a little bit once we start getting past like sophomore level in college. That's a terrible way to put it because nobody's at the same exact level anymore. Once you start getting past like differential equations, it starts getting a little iffy. Mostly just because I haven't taught it for any amount of time. Right, and last time I was a student of that kind of higher level math was at least 10 years ago. But hey, give it a shot. See what we got. All right, so if we do inverse tangent of, and I'm going to do this in, it doesn't even matter what mode I'm in, but we'll make sure that I'm in radians. Yeah, cool. What you need to get good at is cake. I have the cake problem, but cake numbers are very interesting. So these are the numbers of pieces you can slice a cake into given a certain number of cuts. It gets ridiculous. I think it was maximum number of pieces that you can get. All right, so if we do inverse tangent of 2 plus inverse tangent of 1/3 and then we take the sine of that in radians. In radians, we get a value of 0.0 9, 8, 9, 9, 4, 9, 4, 9, 3, 6, 6, 1, 1, 6. And like this just keeps going. So we don't need to really multiply it out like that, but you know, sometimes it helps. Multiply this value by 5 times the square root of 2. Oh, I did it right. Oh, she purdy. Uh-huh. That's 7z. Woohoo! Alright, 3 left seconds. Thank you for the follow. Studying for the ASVAB. Alright. I took the ASVAB twice, I think. And the I was very good at like academic stuff, which is not really that surprising. I was awful at a lot of the non-academic stuff. Yeah. I was going to potentially look into options to do the nuclear program in the Navy and do nuclear engineering as a bachelor's. And then the recruiter practically pissed himself over the fact that my score was so high on some of this other stuff. And I'm like, really? You're going to be... Okay. You can be impressed, I guess. He was like, oh, I've never seen a score this high. I'm like, that's not a selling point. So I was in this meeting with my mother, and I just kind of like looked at her. She was like, oh. Absolutely. Yeah, and I had taken the nuclear engineering merit badge in Boy Scouts, and then I went to the recruiter station and I took the nuclear engineering entrance exam for the program. So I mean, it's intended to be given to high school students, and I was 18 at the time, and senior in high school. And he gave it to me, and I ended up getting a 48 out of 50. And again, he started just, oh, this is amazing. And I'm like, but again, it was because I had a scoutmaster who worked at Seabrook Station. Seabrook Station, the nuclear power plant in New Hampshire. So of course we were gonna, be able to understand all this awesome stuff. Anyway. So Blainland, really quick, this was going to be what we get here. So if we just make up something like this, we end up with a cross product that has these kind of nasty values in it. But when you multiply them all together, it actually ends up getting us just 7, which really makes it very nice. And again, it's 7, but it's in this direction, whereas your 2 vectors were along this plane. So 7 up. Okay, so 3 left seconds. It kind of depends on what you're looking to, like which area of math you're looking into. Like if you got a question that's from the ASVAB, or like from the prep stuff, we can work with that. Yeah. I know that there's the arithmetic section, which is like, do these as fast as you can. That I cannot help you with. It's just going to be a matter of like knowing how to do things. The good news is that those ones are super quick. Like it's just, 12 times 4, 12 times 8. Do you know your multiplication tables, basically? And if you don't, it works okay. But, I mean, we could just do multiplication real quick. So this is a thing that Common Core is actually good at. If you wanted to multiply a big number by a smaller number, there are a few different ways to go about this. And you pick the one that's useful for you in whatever you're doing. So in this particular case, you could go about this in 3 different ways. Or, I mean, there's more than that, but 3 different ways are usually the ones that are used. One is called the standard algorithm, which is what I learned growing up, and which is probably what a lot of you all learned, which is you take 6, you multiply it by 4. You get 24. Carry the 2. You get 6 times 9 is going to be 54 plus 2 is 56. And 6 times 3 is 18 plus 5, wow, is going to be 23. See, I jumped a step in my head. So you get 2,364. Okay, but that took kind of a long time to do. So there might be a faster way. One is the decomposition method. So this is standard. All right, so standard algorithm here. Ugh. All right, so decomposition method is you say that this is going to be 300 plus 90 plus 4 all times 6. Distribute. This is going to be 300 times 6 is going to be 1,800 plus 90 times 6 is going to be 54 tens, so 540, plus 4 times 6 is 24. Add them up. Right, so 1,800 and 500 is 2,300, plus the 40 that we had left over from here, because we didn't touch the 40, plus the 24. Now, all of this I would expect you to do in your head like practically nothing. As long as you can keep them organized, and that's really the big problem here, is just organization. So 1,800 plus 500 gets you 2,300, and then the 40 just comes down. 40 plus 64, that's 40 plus 20, is going to be 64. And then 2,300. So, you get the same answer. Yeah, so this is the kind of thing that, like I said, Common Core does. The reason that Common Core does this is because this extends directly into algebra. So, you want to know what, like, 3x plus 9, I don't even know. 3x plus 9y plus 4 all multiplied by 6 is? Guess what? It's the same thing as this. You got 18 x's. You got 54. Come on now. 54 y's. And then 24 ones. It's just that up here, we called those 3 hundreds. Down here, we call them 3 x's. Here we call it 9 tens. This is 9 y's. Yeah. All right. So like that kind of arithmetic, you could say, all right, if you get two donuts get you 0.33, right? and then a dozen, which is 12, is going to get you $1.74. We want to know if we take this and extend it to 12, right? What's that going to get us if it's just directly proportional? So this is its own thing, right? This is its own separate thing. But now we'd say if we get 2 for 33 cents and extend that to 12, the easiest way to do this is to do proportions. So you say this is going to be 2 goes to 12 by multiplying by 6. So 33 cents needs to be multiplied by 6 in order to get up to this price. Okay, so then the other way we could do it is by saying, okay, I'm doing 2 is going to be 33 cents, which is equal to 12 going to whatever our price is here for a dozen bought this way. Again, here, if we go this way, this is multiplying by 6. So if we go this way, this also needs to be multiplied by 6. So 0.33 by 6. Oops. Raised to a power. Come on. All right, this gets us a total of $1.98. I could have done it in my head and all that, but so $1.98 versus $1.74. Then you want to compare how this all works. This is way outdated, by the way, because Dunks sells all this stuff for way more than that. And if you go to Voodoo, forget it. It's like $10 a dozen, at least. Yep. That's the exact same thing. Because if you're multiplying 2 by 6 to get 12, that's going to be the same as dividing 2 by 2 and then multiplying by 12. Right, so if you divide by 2 and then multiply by 12 as separate things, right, dividing by 2 is the same as multiplication by 1/2. And then multiplying by 12 is 12 over 1. And it doesn't matter if you take your original price and don't do that one. Oops. 0.33, right? So it doesn't matter if you take your 0.33 and then multiply it by 1/2 by 12, or if you multiply your 0.33 by 1/2 first, and then multiply by 12 after. So this is what's called associativity. So these can associate with each other in either order because the operation that's being done is allowed to trade. You can choose what to do first. Doesn't matter. Does the same thing. So associativity really just says, if you want to generalize this, you can say that we have A times B times C, and whether we multiply A times B first and then multiply by C, or multiply A by do B times C first, that's going to get us the same result. So that's the algebra that falls into this, in saying that we can do this in either direction. So you pick, that sort of thing. Well, so we got it down here, right? So if we just buy the dozen, we get $1.74. If we buy all 12 separately in batches of 2, then we have to pay $1.98. So how do you find the difference between the two? Mm-hmm. Yep. Yep. So 198 minus 174. We end up with this $0.24. Yep, so what is the closest prime number to 100? You can look at this in terms of either you just know what prime numbers are, or you know how to find prime numbers. So Eratosthenes, way back in the day, he was one of the people to originally find out that the Earth is, well, no, he didn't find out the Earth was round. It was suspected that the Earth was round anyway, because the Greek Empire stretched over a wide portion of the Earth. So in Europe, all the way around the Mediterranean. So they had. I'm going to go on a little pontification here, so bear with me. So they spanned this empire over several lines of latitude. And they noticed that, especially the scholars who traveled and the merchants who traveled from place to place along the empire, noticed that the sun would reach its zenith in the summer at different angles. So in Alexandria, in Egypt, the sun would get almost 100% directly above the well in Alexandria, which dug seriously deep into the earth to get their water. So you'd be able to see the sun going all the way down the well in Alexandria. Almost 100% perfect circle. If you went to Greece and went to, Athens or wherever, and you did the same experiment there, find when the sun is at its zenith, you'd note that it's ever so slightly off from being vertical. And so they said, well, that's interesting. That must mean that the sun is tilted at an angle in Athens compared to Alexandria. So let's find the angle. And they said, well, if you had Athens here, and Alexandria here, and again, the sun is ever so slightly tilted in Athens compared to Alexandria. Oops. Nope. These lines would be parallel, and then the line that runs to the center, we could assume, in this particular case, that the Earth is roundish. If it's roundish, then it's going to have a center point, like this. If we know what the angle is in Athens between the actual well and the sun, then that is the same as the angle between Athens and Alexandria. And we have merchants who know that this distance is some number of miles. Really cool stuff. So if we know that, then we could say, okay, well, if this is truly a circle, if it is spherical, approximately, then we can figure out that the radius here and everywhere else is this certain amount. So if it is perfectly circular, we have formulas that we can use to make all this work. Eratosthenes was the first one to come up with that value. And he said it was somewhere around like 21,000 some odd miles, which is within 2% of its actual value. Keeping in mind he did this over 2,500 years ago, that's pretty good. And he didn't have the use of, satellites. Nor did he know that the Earth actually is not 100% spherical, but is smashed a little bit because it spins. And like a clay on a potter's wheel, it gets thrown outward a little bit along its or around its spinning axis. Anyway, so Eratosthenes had another claim to fame, which was he started with a list of just all numbers. So I'm going to stop there. Right, and he could list as many numbers as he wanted. I think most of the time I see lists out to 100. I'm not going to put you through that. And he said, okay, if I find a prime number, then what's going to happen is that every multiple of that number cannot be a prime number. So the only factors of a prime number, therefore, are going to be 1 and the number itself. And like I said, all multiples of that number will be crossed out from this list and cannot be prime. So if we say that 1 is prime, then all of its multiples would need to be crossed out, but that's literally every number. So 1 cannot be prime. All right, 2. If 2 is prime, then all of the even numbers, 4, 6, 8, 10, 12, 14, 16, 18, 20, etc., will not be prime. That's okay. It leaves some other ones. So, yeah, all the ones in this column, and this column, and this column, this column, and this column are not prime. 3 is the next number. 3 can be prime. And then we take all multiples of 3. So that's 6, 9, 12, 15, 18, 21, 24, 27, and 30, etc. 5 can be prime, which means that all of its multiples, which end in 5 or 0, are not prime. The 10s are already taken out, but the 5s, all the rest of the 5s are now gone. The next number is 7. 7 becomes a little tricky multiple, but it works. All right, so then we look at 7, 14, 21, 28, etc. Those all get crossed out. 35, 42. And then here, the next number after that is going to be 11. So then 11, 22, which is already crossed out there, 33, 44, 55. It's all going to be crossed out that direction. 13 is going to be a prime number, and next one beyond that is 26, 39, 52, and then it keeps going. The next one after that is 17, and then multiples of 17 are all crossed out, etc. So this gives us a list of all prime numbers that will ever be. You just have to get to them first and cross out all the multiples of all the other numbers that you get. So prime numbers are going to be 2, 3, 5, 7, 11, 13, 17, 23, 29, 31, 37, 20. Where'd that come from? 37, 41, 43. This is where I start slowing down. 47. 53. Yeah. 59. 61. 67. 68. Well, damn. 71, 73. I think 79. 81, 83. $89. 91 is not, because 91 is a multiple of 7. Right, 70 and 21 added together. So 93, 95, 97. I think 97 might be prime. Alright, this is an infinite list, so it just keeps going on forever. I think it's 97 would be the answer to that one then. Oh. Closest prime number to 100, not closest that is less than. So I think that 101 would then be I think 101 would be your closest prime number to 100. I mean, we can always just go on to, you know, Google or whatever. Yeah, 101. So if you wanted the closest prime number to 500, right? It's going to be a little iffy. So you start from 500, and you say from here, what other numbers could I possibly get to using common multiples? So like, any even number is out. That's just immediately, right? All even numbers are gone. So this leaves 499. Let's do it this way. 497. 495 cannot be because it's divisible by 5. So 493. Let's just leave it there, right? Create a candidate list of like 3 numbers to each side. 501, 503, and 507. All right, now I know for a fact that this one and this one are divisible by 3. Easy way is you add up all the digits that are in it. So 5 plus 0 plus 1 is 6. 6 is divisible by 3, so therefore 501 is divisible by 3. Now, you don't have to believe me. You can also check it, right? So 501 divided by 3 is going to get us a 1 with 2 left over. This is a 6 with 2 left over, and 3 into 21 goes 7 times. So 167 times 3 is going to be 501. So out. So that leaves 503 as a possibility, or the ones that are lower. And again, from 501, we could also say, let's subtract 3. So that's going to be 498, and then 495, and then 492, and then 489. Okay, so those are all out. Upward is going to be 504, which was out anyway, and 507, which is now out. So 503 is still a candidate. And you can think, okay, do I know any values that are going to easily divide into 503? Right? I can't think of any. Look at your prime candidate, or look at your prime list, and like one of the things that you can do. Are you allowed a calculator? I don't remember. No. Okay. So if you're allowed a calculator on this, which you aren't, if you're ever allowed a calculator on a question like this, if it's just like a quiz question or something, one of the things that you can do is just like plug into your calculator as a function 503 divided by x, and then see how far you can get before it, like, are there any of these numbers which divide nicely? Not looking like it so far. All right. So there are divisibility rules for numbers, just in general. So again, like we said, anything that is divisible by 2 ends with an even number. So 0, 2, 4, 6, or 8 will be the last digit. So anything divisible by 2 has an even last number. 2, 4, 6, 8, 10. 0. So 500 clearly is not prime, just by itself. I mean, in many different ways, it is not prime. So then we say, okay, this is not prime, but 501 is not prime because we can add its digits up and get a multiple of 3. That is how you tell whether something is divisible by 3. To tell whether something is divisible by 5 is, again, the last digit is either a 5 or a 0. To tell something is divisible by 7 is, quite frankly, evil. So I don't like doing it all that much, but you got to do it eventually. Either you can just try to divide by 7, or you get a number that's close that you know is divisible by 7. So I would know that 497 is divisible by 7. Because 49 is divisible by 7. And then we have a 0 remainder and a 7 as the last digit. So that's going to be divisible by 7. So 497 over 7 is going to be 71. So that's out. Which also means that 499 and 493 are not divisible by 7 because they're too close. All right. 11. Basically, if every other number adds up to the same thing as the opposite every other number, it's divisible by 11. It's really an awkward way to describe it, but 495, for instance. The 4 and the 5 add up to 9, which is the other number. In 1230, this would be 4 here, and this would be 4 here. 1232 is divisible by 11. So I can know that pretty much off the top of my head, because again, every other number adds up to the other every other number group. So here again, 9 is what 4 and 5 add up to. In this case, 1 plus 3 adds up to 2 plus 2. So over here, right, 495 is divisible by 11, so it's not that one. The rest of them I'd have to try, really. Like, what's even going to be 13? 39, 52, 520. So if we backtrack from 520, we subtract 26. That's going to be 494. So 494 is even anyway, and that's your divisible by 13. So that's out. Divisible by 17, I have no clue anymore. I'm just pretty much helpless on this. Yeah, so this is the divisibility thing, which is kind of evil. So divisibility by 7. We said 497 is divisible by 7. Take the last digit, subtract it, double it, and subtract it from minus 14. So get rid of the 7, double it, subtract it from 49, we end up getting 35. Take the 5, double it, subtract it from, never mind. Right, it's 35. I should know this. It's 35. And if 35 is divisible by 7, which it is, then 497 is divisible by 7. Yeah. It's a pain in the rear. All has to do with like times 10 to the whatever and stuff like that. So at this point, right, if you're not kind of coming up with anything really quickly, you know you need to move fast because this is a time test. So if you can eliminate all the easy ones first, get again up through like 11, and you've eliminated all the rest of these that are around it, 503 and 499 are your best guesses. 499's closer. Sure, let's go with 499. Is it guaranteed? No, absolutely not. But is it close? I mean, no, is it good enough for this? Probably. So, let's see. I'm going to try it now. So if we go to 499 over x, and then we do 503 over x, and we do a table. That's not what I wanted. Okay. Nope. Start with 1. Go by no. Is not what I want. Go by 1s. Okay. So I'm not getting anything for either of these. And I have gone out to I've gone out to at least, here's the other thing. You don't need to check very far. So you don't need to keep going into like the 30s and 40s and 50s and stuff like that. What you can do is say, I need out to 500. So when I do like factor lists, right? If I want to know what the factors of 400 are, right? I'm going to go, okay, this is supposed to be 1 and 400, and 2 and 200, and 4 and 100. All right, it's not divisible by 3, can't do it. It's divisible by 5. It'll not be divisible by 6. It won't be divisible by 7. Right, because it would have to be divisible. Sorry, 40 would have to be divisible by 7, so that's not going to work. 8 is going to work because 40 is a multiple of 8, and the last digit is a 0. So that's going to work there. Again, divided in. 8 into 40 goes 5 times with a 0 on the end, so 50. 5 goes in 80 times. Okay. 9 isn't going to work. 10 is going to work. 10 by 40. 11 is not going to work. 12 is not divisible by 3, so that's not going to work. 13, 14. 14 is not going to work because we are not divisible by 7. 15 is not going to work because we're not divisible by 3. 16 will work. Because here we've got 4, and this 100 has an extra 4 to spare. You can trade out your factors. So if we take a 4 from 100 and give it to the other 4, we make 16 by multiplication. And we've taken a 4 out of 100. That leaves us with 25. All right, and then we want to look for other types of combinations here. We're not going to get anything else, really. 20 and 20. So if I wanted to keep going with this factor list, what would happen is that our bigger numbers would start going on this side instead, and we just end up repeating ourselves. So we don't need this. So what's happening, again, either in my little notes that I write to myself over on the side or just in my head, depending on how big the number is, I'm trying to trade around factors and see what's left. So in this case, 400, I know is 20 by 20. So here, I'm going to start breaking down 20 into whatever pieces I can and putting them into different combinations. So this should be all the different combinations we have. Out of 20, you can get a 1, 2, 4, or 5. The fact that we have two 20s here allows us to bring, 4 by 100, give another 2 from 100 to 4 to make it 8 and 50. Give another 2 from 50 to 8 to make it 16 and 25. Just trade stuff around. If we make the left side just 4s, then we've got our 4 here, leaves 100, and then 16 leaves 25. If we do 5, right, from here, give a 4 from 20 to the other 20, make it 80. 5 times 80. You just kind of trade stuff around. All right, what am I doing? Why am I doing this? So if we wanted to figure out what what the closest number was to 400, closest prime number was to 400, what I'd be doing is I'd look at this factor list and say I only need to go out to something pretty close to 20. So if I look at 400 and I want, 401, 403, and then 399, that's not going to work, 397, etc. All right, 399 is divisible by 3. That's out. 402 will be divisible by 3, which is already out because it's even, so that's gone. No worries on that one. All right, so like 401 is close and 397 is close. Those are our two candidates. We want to figure out if there are any prime numbers that divide into them. Because 400 has a square root of 20, this is where the factors start repeating themselves. If you don't find a number before you reach 20, you're not going to find a factor. This is a prime number. So 397. 397 is not divisible by 2 because it's not even. It's not divisible by 3 because when you add up the digits, you do not get a multiple of 3. You get 19. So that's done. 5, it doesn't end in a 5. 7, this is one of the tricky ones. So double. I mean, realistically, the first two digits should be divisible by 7 if the last digit is also divisible by 7 if in a 3-digit number. Just doing it either the divisibility way we talked about before, double 7 to make 14. Subtract 14 from 39, you get 25. 25 is not divisible by 7, so the whole thing is not divisible by 7. Cool. 11, all right, this is 3 and 7 makes 10, which is not 9. So that one is not divisible by 11. How about 13? I don't know. So at this point, I would have to actually rely on dividing it. So 13 into 39 goes 3 times evenly with 0 remainder, and then you've got 7 left over as a remainder. Can't do it. So not divisible by 13. 17, do the same thing. So 17 times 2 is going to be 34, which leaves us 5 remainder. And so the next number is going to be 57. Is 57 divisible by 17? No. Right, it is 51. Right, 51 is divisible. And then the next number is 23. So that's too high. So, this is a prime number. 397 is a prime number. That doesn't mean it's the closest. We got to check 401 as well. So with 401, we do the same thing. All right, not divisible by 2, 3, 5. Not divisible by 7, because there was one that was close. Yep. I guess we didn't figure it out, but whatever. If you divide by 7, right? 40 divided by 7 is going to be 35, 5 left over. 7 does not go into 51, so no. 11, we got 5 and 0 when you add up the every other number, so not divisible by 11. 13, again, this is going to be 39 is the closest multiple, with 1 left over is going to leave 11. Can't divide into 13, so not going to work. 17. 17 into 40 goes twice, which makes 34. With 7 left over is 71. So 71, is that a multiple of 17? I'm going to say no. You do 4 times, it's going to be 40, 68. So 68 is as close as we're going to get to 71. It's not going to divide evenly. And then we got 23. 23 is too big. So 401 is going to be it. Now, granted, right, that took me a minute, but radical specifically, so like that, whichever direction it is. Yeah. So here's the thing. This is an enumeration. It tells you the quantity of things that are here. This is also a number. But more importantly to what's going on here is that this is a unit. This tells you how many of these you have. So don't think of it as like square roots of 2 or whatever. You can do stuff with them, but what's more important for being able to combine them is, are they the same thing? You cannot add apples to oranges in this context, right? We want to know how many apples we have. You cannot add oranges to them. So, if we take this, the square root of 12 can be broken down into the square root of 4 times 3. So this is going to be 3 square roots of 2 minus 4 times, and here this is equal to the square root of 4 times the square root of 3. So some more algebra. A times b all raised to the nth power is going to be equal to a to the n times b to the n. How does that help here? Well, it turns out that the radical, square root specifically, is an exponent. It's an exponent of 1/2. So we're raising 12 to the 1/2 power, which is the same as raising 4 times 3 to the 1/2 power, which by this is the same as raising 4 to the 1/2 power times 3 to the 1/2 power. 4 to the 1/2 power is the square root of 4. It's 2. So 4 times 2 times the square root of 3. This is now 3 square roots of 2 minus 8 square roots of 3. You look at the units. These are square roots of 2. These are square roots of 3. They're not the same thing. You can't add them. You can add their decimal approximations and get a different number, but that's not what this question is asking, I'm guessing. right? Try and simplify the following. That's as simple as it gets. That's it. Now, if you had like 8 root 3 plus 6 root 12, this one does break down further. Again, just the same as the one up above. Root 4 times root 3, 6 root 4 times root 3. 8 square roots of 3 in there. This is 8 square roots of 3 plus 6 times 2 square roots of 3. Okay, so this is 8 square roots of 3 plus 12 square roots of 3. Right? This is how many of these things do we have? We have 8 square roots of 3, and we also have 12 square roots of 3. So they have a common unit. So if we have a common unit, you could just put them outside and say, all right, look, we're doing 8 plus 12. So that's going to be 20 square roots of 3. So treat all of your numbers as if they have an enumeration portion, which tells you the quantity of things that are there, and then also a unit, which tells you what kinds of things we're talking about. Guess what? Same thing works with fractions. Right? A numerator tells you quantity. A denominator tells us the size of the units. The denominations. So if you remember, just talking about like cash, right? Your denominations of money are usually $100 bills, $50 bills, $20 bills, $10 bills, $5 bills, $1 bills. Then we go down into coins, and you've got quarters, dimes, nickels, and pennies. At least most common, right? We'll leave it there. So the denominations are all those values. 1 cent, 5 cents, 10 cents, 25 cents, $1, $5, $10, $20, $50, and $100. So the denominators are just telling you how big are the units that we're using. So you want to do like 8/13ths or something like that. This is telling us that we're going to split something into 13 parts, and we're talking about 8 of them. There we go. Totally 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Cool. And we're talking about 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. Right, and they're supposed to be equal to each other, but I can't draw that, so... Ah, gotcha. So you want to break those up, right? And you say, what do these break up into? Well, 36, you probably should be able to recognize what a perfect square looks like. So either we can break this up into like, okay, it's going to be 3 and 12, or it's 12 is going to be 3 and 4, 4 is 2 and 2. So this should be kind of suspicious. you should say immediately, hey, I've just circled all of my numbers, which are the like edge branches for this particular number, 36. That means that 36 is a perfect square. If you already know what it is, right, square root of 36 is 6, so that's nice. We're subtracting that from the square root of 108. Here, you can do a few things. One, again, we're trying to get rid of perfect squares. So try to divide out try to divide out any perfect squares we have. Perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So in this particular case, also note that 1 plus 8 is going to get us 9. 9 is a multiple of 3, but also it adds up to 9, or a multiple of 9, which means that it is divisible by 9. It's one of those weird quirks. Absolutely love it. So if we divide by 9, we get 9 out of 10 leaves 1, and then 9 out of 18 leaves 2. So 9 times 12 is going to be our value that we get for 108. If you already know what it is, again, there's a 4 and a 3 from 12. A 9 and a 4 are perfect squares. So take them out, or at least move them up. So this becomes the square root of 9 times 4 times the square root of 3. Here, 9 and 4 are going to make, when you take the square root of each of them, 3 and 2. So that's going to be 6 root 3 minus 6. If they just want it like this, that's as much as you have to do. If they want like a factored form, I don't know why they would, but just to check that you can do it. Okay, we can make it 6 times the quantity root 3 minus 1. So what are its factors? We've got 3 and 3 and 2 and 2 at the ends here. So because it has 2 of them, or 2 of each of them, it's going to end up with 2 branches that are the same here, a 9 and a 4. Right, I just happen to know the perfect squares because, I mean, going way back, I knew the perfect squares a long time ago just because I found this stuff fascinating. This is like before I even understood what multiplication was. I could like just pick out the perfect squares because I could arrange objects into these shapes, or into a square shape. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. So those are the first 10 perfect squares. Yeah, you can, but then you want to break down 18 further, because 18 is not a perfect square. So if you split up 36 as 18 and 2, then you're going to split up 18 as 2 and 9. And again, 9 as 3 and 3. So again, here you've got 2 3s, and here you've got 2 2s. So if I come up with all right, 3,249. Right, we want to take we want to take a square root of this number. I don't know offhand. So for this, I would start falling back on my divisibility and saying, can we add up any particular numbers? Is there anything nice about this that we can figure out? So I did something. No, that's all right. So here, 2 and 4 is 6. 3 makes 9, and 9 is going to make 18. So this is going to tell me immediately that this is divisible by 9, because it's going to multiply. So the digits add up to a multiple of 9. So I'm going to take a 9 out and find out what's left. A 9 is a perfect square, right? It's 3 times 3. So we're going to keep that. And then when we divide out the 9, we get here 27 is the closest. So that's 3 with 4 left over. 9 into 44. Ugh. So close. 9 into 44 goes 4 times, which gets us 36. To 44 is a remainder of 8. 89. Man, I messed that up. Oh, 27. Remainder 5. That's what it is. 5. Oy. So, again, what you can do, the divisibility rules that I was talking about before, you can add up the digits that are here. So 3 plus 2 plus 4 plus 9. When you add them up, we end up getting a 5 plus 4 is 9 plus 9 is 18. Since 18 is divisible by 9, then 3249 is divisible by 9. All right, with 5 left over, 54 goes 6 times and then a 1. Yep. So a 9 and a 361 are going to be the two terms that we have here. Now, I don't think 361 is going to be divisible by anything useful. I guess it could be. No, divide it. Like, actually do the division. So if you need to do it on the side here, right, 3249 divided by 9 is going to get you, again, 3, which is 27, which leaves 5 as your remainder. 9 into 54 goes 6 times with a 0 remainder, and 9 goes into 9 once. 361. Right, so 9 and 361 become the factors. And then 361, you want to check, are there any primes that I can square that are going to get me this value? If you can, great. If you can't, then it doesn't matter. So you kind of run through the prime list and you say, do any of these, when I multiply them by themselves, end up getting a 1 at the end? So, oh, I missed one. Ah, 19. Great, now I got to check 401 all over again. All right. So here, we want to know if this is divisible by 19. I don't know a rule for that. So the fact that it ends in a 1 is a possibility. I would have to probably, excuse me, manually divide it out to try to figure out if it's divisible by 19. I don't know if I want to do that, but I can say, what's 19 times 19 just as the perfect squares? So 9 times 9 is going to get us 81. 10 times 9 is 90, and 10 times 9 is 90. So add them up, it's going to be 180, plus 8 is 188. What the hell? Oh, I just screwed up. Hang on. All right, so this is going to be, 9 plus 9 is 18 plus 8 is going to be 26. So, nope, carry 2. And then here, hundreds place is going to be tens by tens. Is 1 times 1 is 1, plus 2 is 3. So it is. It's 361. So this is 19 times 19. So this is a perfect square. The value that we're going to get out of this, the square root of 3249, is going to be equal to the square root of 9 times the square root of 19 squared. So that's going to be 3 times 19. So that's going to be 30 plus 27 is 57. So you can, that only tells you whether or not it's divisible by 3 or a multiple of 3. So 3 plus 6 plus 1 is 10. That's not a multiple of 3. So that's it. We're done. That's the only thing you can check. And as it turns out, right, the numbers that we get for this, the only factors that we get for 361 are 19 and 19. So not every method is like a catch-all for everything. It's just going to be like it checks for a specific number or a specific group of numbers. That's all it can do. My guess here was, since this value ends in 1, and we know that we have to have a perfect square, then it's got to be the last digit has to be what happens when you multiply together your last 2 digits. So if the last digit is 1, then we're going to end up with a 1 as our ones place. So that would work. So then we look at it and we say, okay, can we get 11 to be 11 squared to get 361? Well, no. 11 squared is only 121. Not going to happen. Could we get 21 squared? Well, 21 is bigger than 20, and 20 squared is 400. So it's bigger than 361. We're not going to get a 1 as our final digit. So do any other numbers, when they square, get a final digit of 1? So 2 squared is going to be 4. 3 squared is going to be 9. 4 squared is going to be 16, ends in 6. 5 squared is 25, ends in 5. 6 squared is ending in 6. 7 squared ends in 9. 8 squared ends in 4. And 9 squared ends in 1. So the only other possibility here was, okay, we know it's not 9 squared, so 19 squared. 29 squared, again, is too high. So it's got to be 19 squared, otherwise it's nothing. There's no way to get a perfect square. And if it wasn't a perfect square, I was just going to let it go. Because that's perfectly possible. We don't really care whether it has factors of, like, 23 and 15 or something like that, or 23 and 17. 23 and 17 are prime numbers, so they're never going to come out of the square root. The only things that can come out of the square root are perfect squares. Everything else we just want to leave together underneath. All right. Any more questions? We're running up against 12:30 here, so it's It's not like it's my bedtime or anything, but... Honestly, I probably should be responsible and go to bed, but that's not happening. Oh, I know who we're raiding tonight. Alright. Alright. So a couple of last things here. Shout out again to Vainglorious Gaming. This is Brandon. Brandon is an awesome streamer. He does a lot of stuff like Astroneer. He's playing Timberborn lately. He's one of our stream friends and really awesome guy. So go and check him out. We've also got a number of other people. Those of you who are interested in mathy type streams, we have Megalomorph, who stops in occasionally here and streams science and technology, but really it's mathematics. So you can go give him a follow, and we don't... He kind of is a little more sporadic lately. And I believe I'm spelling this correctly. We'll see if it works. I spelled it wrong. Okay. Tayo Inoue is a streamer who also does math. He shows up every so often. I always try to stop in whenever he's in. Oh, no Y. That's what the problem is. There we go. So you can give him a follow too. He usually does pen and paper on a document camera. And does like problem type after problem type. And so I really like Tayo. I don't see him too often, but you know, everybody decides their own stream schedule. And if he's not getting much of a following, I know it can be kind of frustrating. Or if Twitch is taking all his money. I know that lately it's becoming more of an issue where streamers are getting less and less of a market share, despite doing more and more to try to gain some money off of the stuff. I pretty much am making I am under no illusion that this stream is going to make any money. So, so I don't think that I will ever do, you know, sponsored segments or anything like that unless somebody comes around and is like, try my game. In which case, I will run a Friday night stream. I will let you know exactly what is going on. I mean, legally I have to, but I will let you know exactly what's going on and whether or not it's sponsored. I have not had a sponsored stream. I will probably not have sponsors because, quite frankly, I only get about 5 to 10 people every stream coming in and checking it out. So, probably no worries from me. I will say, hashtag unsponsored. Hashtag unsponsored. My coffee tonight. My coffee tonight is from a company called Coffee del Cerro, which is a Honduran kind of guy and sons company um, who does awesome coffee. Um, I met the eldest son. His name is Enoch, and he was at a farmer's market in, somewhere around my area. And so they work out of Baltimore. And he came, I don't know, half hour or something like that over to this farmer's market nearby. And he um, was just there with his spouse, and they like gave people free samples of their coffee. And then this was like early days of the pandemic, so I was really kind of sketched out about taking a sample, um, touching stuff and things like that. Nobody knew what was going on at that point. So I was like, well, I talked with him for like a half hour about his coffee, and ended up uh, like buying two on the spot and then just going to his website all the time and purchasing. So the first time that I purchased from his website, I purchased like on a Saturday night, and then Sunday morning he was out at another farmer's market. I didn't know this. He showed up at my door, dropped off the box of coffee, and just, rang the doorbell and left like anybody else from Amazon or UPS or whatever. So I came outside and I look at the thing and I see the return address and I look up and he waves at me. I'm like, "Oh. Oh." So, it's Enoch. So it took me a minute to register, but it's the guy from the coffee company. Like, physically delivered this thing to my house. It was really cool. He doesn't do it anymore, really, because he's just got a lot of other customers and time and stuff like that. And he's never around here when he needs to, like, when he's at the farmer's market. I don't think he's at this farmer's market anymore. Or, he only comes to it every so often. So they ship in. But at any rate, it was. I really love their company. I really love their coffee. And I let me tell you, I grind it down to a fine, and I use a metal disc disc filter that goes into the AeroPress, and it lets some of the solids through. So like my coffee is mud basically. But when I pour the water in, it like settles all by itself. It's really great. I love it. It's aerated properly. It's got oil in it. I mean, not like it has coffee oil in it, but it's really noticeable, and I love the flavor. It's one of my favorites. So just throwing that out there if anybody's interested. I don't have any specials or anything like that, but like I said, hashtag unsponsored. This is not cleared by their company or anything like that. I just really love their coffee. So if anyone is interested, this is that. So I just really like them. They're nice people. They run this business where they have the father and his two sons. His two sons are now running it. The father helps out on the farm, but for the most part, he's retired. Um, and yeah, so Enoch's brother Cesar is currently in, as far as I know, in Honduras, like operating the farm. He's the manager of the farm that's there. Anyway, I am going to raid out to Selena, who is playing Super Metroid. So this is one of the games that I started speedrunning like way back in the day, and my brother is actually big in their speedrunning community. So Super Metroid is really awesome. I love the game, and Selena's really funny, and she's got all great emotes and stuff like that. So have a good night, everybody. I will see you on next Tuesday for math, or this Friday for games. So hope you all can make it out, and I'll see you later. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.